So this video is about Octet rule when drawing Lewis structures, and I will also cover the exceptions that exist when you're drawing the Lewis structures. We will also talk about single, double, and triple bonds. I will also introduce the concept of lone pairs and bond pairs and tell you what we mean by these two terms. So let's take a look at Octet rule. So Octet rule states that after bonding, every atom needs to have 8 electrons around it. It comes from the Latin word octa, which means 8. So most of the atoms after bonding, they need to achieve 8 electrons, to have 8 electrons after bonding in order to be stable. So of course, there's exceptions for these, and I'm going to cover the exceptions after, but just for most cases, imagine and consider that you have to have 8 electrons after bonding. So for doing that, let's take a look at some examples like PF3. So one thing I want to note over here is the way I'm drawing these structures are very basic. So I don't like this way of drawing Lewis structures. I already have another video that I will tag over here. If you want to learn the easy way to draw Lewis structures to be safe and not to make any mistakes, I suggest watching that video. I'm just drawing these structures very basic by putting the lone electrons or valence electrons on each atom and then start sharing them, which is not the best method that I like to do, but it's just more for you to see the number of electrons after bonding, to see which one has 8, which one has more. So the first example is PF3. So P belongs to group 5. So it's the central atom. So we'll bring its 5 valence electrons. We also have 3 fluorines. So we put them all around. Each of them brings its own 7 valence electrons. And then what happens between them is now they start sharing these electrons because we have a covalent bond between them. And P is a nonmetal, F is a nonmetal. So they start making a covalent bond or covalent bonds. And what happens is after bonding, if you count the electrons on each F, you will notice after bonding, there's 8 electrons. So it has a full octet or a complete octet. So this fluorine is good with 8 electrons. This fluorine is good. And then the last fluorine is also good. So everyone has 8 electrons around them. And then after bonding, we can count the electrons on phosphorus. Same thing. We can see that phosphorus also has 8 electrons around it. So it has a full octet. Now, let's take another, actually, before to go into the next example, I want to show you what we mean by single bonds versus double bond versus triple bond. So when you see these electrons that they're alone and they're not in a form of a pair, these electrons, they like to be shared between with another atom. So for example, what we can do is we can connect those 2 electrons together with a single bond. So what we're doing, for example, between P and F is we're connecting the 2 electrons. So we're creating a single bond. Here we do another single bond, and then at the bottom we do another single bond. So in total, we have 3 single bonds over here. So a single bond is made from a pair of electrons. And these electrons that are involved in bonding, we call them a bond pair because it's made from a pair of electrons and it's involved in bonding. However, we have some electrons on the outside atoms or even on P that they are also in a form of a pair like this one, but it's not involved in bonding. So we call them a lone pair or a non-bonding pair. So here we can say each fluorine has 3 lone pairs on it. And then it's also connected with a bond pair to the phosphorus atom in the center. So a single bond is made from a pair of electrons that it's being shared between 2 atoms. Now let's take a look at an example that has a double bond in it. A double bond is made from 2 pairs of electrons being shared. For example, if you have something like O2, let's say each O belongs to group 6, so it brings 6 valence electrons. The other O does the same thing. And now these electrons that are alone, we can connect them together. And this way we have 2 lines. So we call that a double bond. So as you can see, a double bond is made from 2 pairs of electrons. Now let's take a look at an example with a triple bond. So triple bond is, by the way, the maximum number of bonds you can get. So you can either have a single bond, a double bond, or a triple bond. You cannot have more than 3. So the example is something like N2. So N can bring 5 valence electrons. The other N does the same thing. And then once you connect these 3 lone electrons with each other, we get 3 bonds. So we call this a triple bond. So now we can say N2 has a triple bond in it, and then we can say each N has a lone pair on it. So as you can see, a triple bond is made from 3 pairs of electrons or 6 electrons in total. All right, so then the next slide is about exceptions to the octet rule. So as we said, most of the atoms are happy with having 8 electrons after bonding. However, there are exceptions. I'm going to list them over here first, and then I'm going to go into details of each of them individually. So first example or first exception is hydrogen. Then it's beryllium, boron, and at last is the atoms in the third period of the third row of the periodic table and after, like phosphorus, sulfur, bromine. So as the case of hydrogen, hydrogen is happy or stable with 2 electrons and only 2 electrons, not more than that. Beryllium, on the other hand, it is, first of all, actually, beryllium is a metal. So you might think it doesn't do a covalent bonding, but it can do covalent bonds as well. But when it does that, it's happy with 4 electrons. So it doesn't need to have more than that. So we say it has a complete octet, incomplete octet. Then it's boron. So boron can have 6 electrons again, 6 electrons, meaning it can have an incomplete octet, or it can have 8 electrons. Then in that case, it has a complete octet, but we don't want to push it for more than 8. And then at last are the atoms in the third period of the table, of the periodic table. And those atoms can have 8 electrons, which is a complete octet, or they can have more than 8 electrons, which is, then in that case, we call it an expanded octet. And then with the help of the formal charge, we can find the best structures for them. Now I'm going to go into the details of each exception and talk about them with some examples. So first exception was hydrogen. So we said it's happy with 2 electrons and only 2, maximum 2 electrons. So for example, let's say we have NH3. To do the Lewis structure, we put the valence electrons on nitrogen, 5 electrons. Each hydrogen brings 1 electron. Now they start sharing. After sharing, if you take a look at each hydrogen, now it has 2 electrons and it's stable and happy. So this is good. We do the same thing for the other hydrogen. Again, exactly has 2, good. This one has 2 as well, good, and they all are happy. Now let's take a look at another example, something like H2. Again, each hydrogen brings 1 valence electron. They start sharing. So now this hydrogen has 2 electrons. The other one has 2. They have a full structure that they need. So, and they're happy with 2. So they both are good. Now the second exception was boron, or sorry, beryllium first. So for beryllium, it's a metal. So we mentioned usually metals, they tend to participate in an ionic bond, not a covalent bond. But we have cases for beryllium that it actually does covalent bonding. And in that case, what it does is that it can bring its 2 valence electrons. And then after bonding, it will end up getting 4 valence electrons. So it will have an incomplete octet, but it's happy that way. It's stable that way. So you don't need to worry about pushing it for 8. So it's always happy with 4. And we call that an incomplete octet. So let's say beryllium brought the 2 electrons. Each chlorine brings 7 valence electrons that it has. After bonding, if you count the electrons on beryllium, now it's 4 and it's happy and it's stable. It's good. Now, the third exception was boron. So boron, we said it's happy with 6 electrons or 8 electrons. So if it's 6 electrons, we say it has an incomplete octet. If it has 8, it has a complete octet, but we don't want to push it for 8. So I'll show you 2 examples that where it has 6 and it's happy and when can it have 8. So BH3, for example, if you want to do the drawing, you show the valence electrons on boron, 3 valence electrons, because boron belongs to group 3, so it has 3 valence electrons. Now each hydrogen brings 1 valence electron. After sharing, after bonding, if you count the electrons on boron, there's exactly 6 electrons, and boron is happy and good. The other example is BF4-. So this one is an ion. It has a charge. So for simplicity, I'm actually putting, that means there's an additional electron, and I'm adding that additional electron on boron. Again, this is not the best way to draw this, but I'm just showing you for the sense of electron count, so you can see how we can count the electron afterwards. So let's say boron already had 3 valence electrons. Now because of the minus, it has 4. Now each fluorine brings 7 valence electrons. And now if you count after bonding, you will see boron now has 8 valence electrons. So this structure has a charge. Usually when you do the Lewis structures, when some ion exists, if there's an overall charge, you have to put a bracket and you have to put the overall charge on the outside. And now let's take a look at the electron count on boron one more time. After bonding, you can see boron has exactly 8 electrons, so it's happy and stable. So this is good. And at last, we said the elements that they belong to the third period or after, something like phosphorus, sulfur, bromine. So these guys, they can have either 8 electrons, meaning a complete octet, or they can have more. So if they have more than 8 electrons, we call it an expanded octet. And formal charge is something that can help you to find the best structure, especially for these elements that they belong to in the third period and after. But I will tag another video over here that explains finding how to find the formal charges and to find the best Lewis structure based on formal charge. But for now, this is just to see that in which cases can something have 8 electrons, something in the third period or after can have 8 electrons, and in which cases it can have more. So for example, in the case of SH₂, S is in group 6, so it has 6 valence electrons. Each H has 1 valence electron, so they bond together. After bonding, if you count the electrons on sulfur, it's exactly 8. So it's happy and good. So we say sulfur has a complete octet in this sense, in this case. And then next example would be SF₄. So S again belongs to group 6. So I'm bringing the 6 valence electrons. We have 4 Fs all around. Each F brings 7 valence electrons. So now they start sharing electrons. After sharing, if we count the electrons on sulfur, now we see there's exactly 10 electrons. So now what we say is that S now has an expanded octet, and it's happy, it's okay. It can have more than 8 electrons. The reason it can have more than 8 electrons can be explained based on orbitals. I'm not sure by this point when you're watching this video if you know much about orbitals, the S, P, D, and F orbitals. If you do, then I can explain to you that because elements on the third row, now they start having the d orbitals as well, because in row 1 you only have the s orbital. That was the example for hydrogen, so that's why hydrogen could only have 2 electrons, because s orbital can hold a maximum of 2 electrons. And then on the second row they have s and p, so they can take in total 8 electrons. But after second row, on the third row and after, the d orbitals come in and they have more room. There's room up to 10 additional electrons. So that's why they're okay to have more than 8 electrons around them. So in this case, sulfur has 10 electrons and it's happy. All right, so thanks for watching this video. If you enjoyed it, please don't forget to hit the like button and subscribe to watch more tutorial videos. See you later.